Hi. So welcome everyone. We're pretty close to the end of the workshop. Just 2 more items on the list. And here we got the flat space panel discussion led by Alok, and who has kindly found Jan, Anna, and Suvrat willing to function as panelists. So I will hand over the word to Alok and we'll do a fruitful discussion.
Okay, thanks. And thanks to all the organizers for organizing this very unique workshop and also these panel discussions, which are really interesting. Maybe what I'm going to do is just give you a small like a brief perspective on at least kind of the way I view this subject, flat space holography. And then, by the way, is this screen visible or should I do full screen? Is it small or is it okay? Just do the... Is it fine now? Okay, yeah. So we have 3 fantastic panelists, Jan, Anna, and Suvrat. And so what I'm going to do is give you a sort of a brief, my perspective on flat space holography, and then we will go with Jan, Anna, and Suvrat, and hopefully have a really lively discussion following that. So let me just start with a very basic sort of motivation that, like, the first thing is, how do we understand flat space holography? And here, obviously, we have, unlike Adcft, we don't have any sharp, statement of conjecture of the sort that string theory on, say, for example, 5-dimensional Minkowski space, times some compact space is dual to a gauge theory in a 4-dimensional Minkowski space. So because we don't have any sharp kind of a premise to go with, there are 2 possibilities which people have explored. One is where you think of flat space holography as, in some sense, coming from Adcft, where you take the flat space limit of the Adcft duality in a precise way or in an appropriate way. And the other, which is that you define these holographic duals directly intrinsically in the flat space. So the first one, which kind of, I just call it the first path, where you start from Adcft and you try to define the flat space holography. It started, I think, a long time back. At least some of the papers that I know, it goes back to early work of Giddings and work of Penedones and his collaborators, and then all the way up to, there have been papers even recently by Silvio Pufu and his collaborators. So let me just give you a brief idea of the way I understand this way of approaching flat space holography, because I think it brings out important difference from the way we approach it, directly intrinsically in flat space. So here the idea is that you start with Adcft. So you take Adcft as given and consider some localized sources on the boundary, which are such that, which are designed in such a way that they interact they evolve and they interact in a small region, which I call S here, where the size of S is much less than the ADS radius. And there is a precise sense in which, in these papers of Giddings et al., that you can engineer these sources, at least for scalars, where on the boundary, the width of the source is appropriately modulated in the frequency omega, and the angular spread is also very, very small. And it turns out that then if you evolve these fields, then the bulk field gets localized around this origin, which I just call O here, and it looks like really like a flat space field, where K is just some appropriately defined momentum vector. And already I think interesting stuff has come out of this analysis, in the sense that if you just take this kind of boundary correlators, which are appropriately weighted with the sources for these localized wave packets, and you take the flat space limit, then you see that already, one interesting stuff that comes out is that you get a distributional momentum conserving delta function. So it's a first indicator of how, from CFT correlators, we get a scattering amplitude in flat space times this stripped amplitude. And there has been at least some work on understanding what this stripped amplitude is in terms of the dual gauge theory. And so, for example, it's really like a large n limit of a connected correlators in CFT, but where you keep the G Young-Mills fixed. So it's not the usual planar limit that we do in Adcft, but it is a kind of a interesting limit. And this was explored, at least one paper I know where it was explicitly explored, is by Penedones and Okuda in 2009, where they look at a 2-2 scattering of string states, actually just dilaton states in 5-dimensional Minkowski time sphere, and they showed that just from looking at the connected correlators in this particular limit, you recover this reduced amplitude, which is the amplitude in flat space. So this is really an amplitude which is actually a fixed angle and a high energy scattering. So you have large S, the limit is such that it's large S, but T by S is fixed. And there's a weird large N limit where the 't Hooft coupling is also going to infinity. Okay, at least one thing that I would like to understand better in this analysis is, it's not clear to me what happens with the back reaction on ADS. And also it's really, this analysis, as far as I understand, so far has led to the specific large S, fixed angle, high scattering, which have, but a generic S matrix in flat space will not have conformal invariance. And this really, brings us to the infrared issues in the flat space scattering. So this idea of going from ADS CFT seems to tell us that we can get a class of scattering amplitudes via CFT, but perhaps the ones which are sort of more UV, which are more which explore the UV properties of the amplitude in the sense of large S. So the idea that we want to look at, we want to really look at amplitudes which are more general. And I think the first sort of initiative in this direction was taken by Jan and Solodukin, and there was some work of Marals who showed that the holographic duals should not, they should have BMS symmetries, which are not captured by this ADS CFT approach, where we get amplitudes which have conformal symmetries, but nothing like BMS symmetries. And this was really like a bottom-up approach in the sense that, kind of like bulk reconstruction in the ADS, that, you start with, you want to find boundary representation of bulk quantum fields. So this kind of brings us to the second part, which is, which really, in my opinion, started with these early works of Jan and Solodukin. And so the idea now is that we want to look at develop holography intrinsically in flat space. And already there are subtleties and caveats here in the sense that, okay, so as I guess everyone knows that the boundary of asymptotically flat space-time is more complicated. So you have time-like infinities. You have this very well-known null infinity, which is like the most well understood and in some sense the nicest boundary. And then there is the spatial infinity, which is the closest to the boundary of ADS. But the spatial infinity, there are many representations of it. So there is a representation where it is a point, which is the one that Penrose has developed. And the one that was used by Jan and Sergey was the one where the spatial infinity was a three-dimensional hyperboloid with a de Sitter metric. And there is another one, which is more popular in mathematical relativity community, where it is just an Einstein static cylinder. So, there is no unique representative for this, for I0, and it also, in some sense, complicates some of the issues. But so this is the starting point that, we want to just start with asymptotically flat boundaries and try to develop holography from here. So this is the kind of the second path. And in some sense, there are advantages of the second path that we already have observable in quantum gravity in asymptotically flat spacetimes, which is the S matrix. And another nice thing that happens is that the algebra of boundary operators, which you define, turns out to be free field algebra in the sense that if you look at the algebra of stress tensors in ADS, just the stress tensors themselves, then we can't really obviously analytically, it depends on the theory, details of the bulk theory, etc. We don't know what this commutator is of the stress tensor at generic points B and B prime on the boundary. But the analog of the stress tensor in asymptotically flat setting is what is called this News tensor, which contains the information about the gravitational radiation, and it has really like a free field commutator. It's very, very simple. So somehow this is one thing that happens, which becomes nicer in flat space. The algebra of boundary operators is a much more tractable algebra. So this is the essence of this part 2 is that you look for holographic dual by looking at symmetries of the S matrix, because S matrix is a good observable. And here I want to just share one caution that this is a little bit simplistic in the sense that we know that actually S matrix has infrared divergences, and this is something that we still need to understand a lot better, because so strictly speaking, it's not really a well-defined operator in the theory. But this approach. Yeah, sorry, I just erase a little bit because sometimes, so let me just, it's visible, right? My screen?
Yes. So far.
Okay, thanks. Yeah. So this the second path that I was discussing to define, holographic duals of the S matrix has really seen a lot of work post 2013, because the idea here is that you really want to start, with work of Strominger et al., because it turns out that the symmetry, the S matrix of quantum gravity and asymptotically flat spacetime has a very rich structure of symmetry structure. So especially if you stay below the threshold, formation of black hole, then there is a, already in classical gravity, people knew that there was a super translation symmetry for scattering, classical scattering, but now it has, through work of Strominger and many other people, that we saw also talk in the talk of Laura today, that there is a super rotation symmetry which has emerged, and in fact there may be many more which will come out. So the idea now is that to build a dual theory which expresses the S matrix of quantum gravity, and the dual theory should have all these symmetries, infinitely many, like possibly an infinite tower of infinite dimensional symmetries. So I guess most of you know what some of these symmetries are. So there is a super translation symmetry, which is very well defined on Scry, in the sense completely well understood, and it basically generates angle dependent translations of on null infinity. And there are the super rotations, which are a little bit difficult to define, but roughly speaking, what they do is to deform the metric on the celestial sphere, which I just call QAB here. And super translations are very, very understood in a great detail, in the sense that if you even pick whichever representative out of the two that you can pick for the spatial infinity, whether it's a hyperboloid or a cylinder, there is a nice smooth definition of super translations, at least for a large class of spacetimes, which is continuous and smooth across Cry minus, Cry plus, and spatial infinity. Super rotations are not that well understood, and I think this is one of the things that hopefully in next few years it should become better understood. But okay, because of this fact that at I0 structure of symmetry is not very clear, we could focus on purely massless scattering, like scattering of gravitons, for example, where we can focus on where the in Hilbert space is defined at past null infinity and out Hilbert space is defined on future null infinity. And the idea is that we have these infinitely many symmetries of super rotation, super translations, which are very well defined. And can we build a dual for the, at least let's say for the tree level S matrix of gravity, to start with. And the reason this turns to work very, very nicely is because these asymptotic symmetries constrain the S matrix in the infrared very well. And this goes by the name of soft theorems, which are really exact statements on the S matrix. So if you focus on tree level S matrix, then there is an expansion. If you look at the amplitude for n+1 gravitons, and where you take one of the graviton to be soft, then there is a nice LoRa expansion in the frequency of the soft graviton, which I call omega here, where all these coefficients are really universal, and they don't depend on the details of the theory. F1 and F2 are really universal. They don't depend on the details of the theory, and coefficients after F3 depend on mildly on the details of theory, but in a sort of a controlled way. And one surprise that comes out, which is really different than ADS, is that because of these asymptotic symmetries, we have infinite degeneracy of vacua. So if you take a flat space, just call it Minkowski, then it's not the same as if you added a soft graviton and subleading soft graviton in the soft expansion. So you get a spacetime which is still flat, but it is physically distinct than just a spacetime without the soft gravitons and soft modes. I just want to mention a small thing, that actually there's a hidden magic in amplitudes in gravity, that there are beyond tree level, there are exact factorization theorems which are beginning to be more and more understood, and especially due to work of Sahu and Vishwajit Sahu and Ashok Sen, is that if you took exact n+1 amplitude in quantum gravity, perturbative quantum gravity, then it has a factorization theorem where there are loop corrections, but all the terms, coefficients of these loop corrections, they are exactly well understood. They are universal. They only depend on the asymptotics of the scattering. And so beyond tree level, these factorization theorems seem to have a lot of information. So now the idea is that can we use this asymptotic symmetries to build the holographic dual? And here we really want to use the old ideas of Adcft, that we want to have a symmetry preserving map from symmetries of S matrix to symmetry in the boundary theory. And this is where celestial holography really enters, in the sense that it aims to provide a map from amplitude, in asymptotically flat space-time, to correlators, conformal correlators on the boundary in terms of some fields which are with weight deltas, such that, I mean, the key point here is that whatever symmetry structure we have for quantum gravity as matrix, that should carry over to currents in the dual theory. And this is something that I think Anna will, at least some aspects of this Anna will touch upon. I mean, one thing that kind of distinguishes it from the usual ADS, the CFT, which is dual to theories in ADS, is that these weights are not necessarily real. In fact, they are just they are complex. And these are some, I mean, there have been some examples which look promising in the sense that although we don't know what is dual to say the generic tree-level amplitude in gravity, people have been able to construct quote unquote duals for sectors of tree-level gravity amplitude. So for example, if you just take MHV amplitudes, then it turns out that there is a sector of a theory which kind of completely can be used, which is built completely out of these currents associated to super translation and super rotation, which can be used to determine the bulk amplitude, bulk MHV amplitude. And then by there is further work to start with this, just these BMS symmetries and kind of bootstrap, and then see how much we can, how much dual theory we can build. So in general, I really, one thing I want to emphasize is that the celestial holography also, I feel that it should be thought of as a bottom-up approach, in the sense that the point is that we are starting with the S matrix in the bulk theory and kind of rewriting it as a boundary correlators in the sense of HKLL, for example, in ADS. So you give me a bulk field, and we write it in terms of some boundary field and some bulk to boundary propagator. And so the approach is perturbative, of course, and it's really a bottom-up approach in that sense. But there is a key difference from although there is a CFT correlator which is dual, which is producing the S matrix, there is a difference from path one in the sense that these celestial correlators are really distributional, and this is something which is different than what work of Steve and Panedones and all was showing, where you had the stripped amplitude was governed by the conformal connected correlators in the CFT, whereas here the celestial correlators themselves have they don't capture stripped amplitude but the complete amplitude, and they use factorization theorems crucially. So they use these asymptotic symmetries or the soft theorems crucially to construct the dual, which was different than we never use any soft theorems in the in path one. In general, celestial dictionary can be used for massive fields also, not just for massless amplitudes. And the reason is that if you take a bulk massive field at some point x, then in principle, if this x is if you're far in the future, then you can rewrite it in terms of again, like HKLL, you can use this hyperboloid slicing in terms of Euclidean ADS3 and rewrite it in terms of the fields on the boundary. But the key issue, I mean, at least in my opinion, one issue which is not properly understood is that there is no extrapolate dictionary for the massive fields. If we go to null infinity, so it's not very clear where these boundary massive fields live. We know they don't live on null infinity because massive fields fall off faster than any polynomial in R as you go towards null infinity. Of course, trivially, you could say that they live on time like infinity, but perhaps for holography, that's not very useful. And so perhaps the most prominent, I mean, the most promising arena where one could have a dual or boundary representation for massive field is spatial infinity. And this is something which was explored in this paper of Jan and also paper of Marolf in 2006. And okay, I just say a few more things now that there is one thing that we should not forget in all this, that the S matrix really is not well-defined operator. So the lot of work which has been done in this path two, where you start with the S matrix and look at its symmetry, we are really looking at tree-level amplitudes. So, but it is known that that if you add loop correction, of course, this S matrix becomes infinite divergent, and in some sense that is also consistent with the existence of these symmetries, because these symmetries tell you that there are infinitely many vacua, and if you go from say scri minus to scri plus, then there is necessarily a vacuum transition. But the precise question, which in my opinion still not been clearly answered, is how do we really define this this quote unquote soft vacua which lead to infrared finite S matrix. So the most commonly known approach is a very old work of Coolidge-Purdy, where the basic idea, I mean, just schematically is that, you take any finite energy state, which is in the Fock space, and you kind of dress it with soft gravitons. And then the resulting states are such that if you compute S matrix, then S matrix turns out to be IR finite. But there is one issue here, and which is the fact that what do we mean by soft integration? So, if we say that we integrate over energies from 0 to delta, where delta is just some cutoff we choose, then we mess with Lorentz invariance. And if we say that, if we just don't worry about it and just integrate over all frequencies, then it can be shown that we don't really get the right classical limit from such dress states. So, so this is something that one needs to understand better. There has been a lot of, I think really promising work in this direction by use of soft collinear effective field theory, especially by work of Schwartz et al. But there is one issue here that although they are able to define an S matrix which has no infrared cutoff, so it's Lorentz invariant, the final S matrix they get for many technical reasons, which which I can't go into here, but which depends on the UV renormalization sliding scale. So even if you start with a renormalized Lagrangian, in the end, the S matrix you get from this approach is really not something which is physical, but it depends on this, on a UV scale. So it is something which is which is not perhaps not the right object to look at for as a physical observable. But of course, you can use it to construct infrared safe observables, like for example, the inclusive cross section. So those are there; those are the right observables to look at. But if our interest is in constructing dual of S matrices, then I think we need to worry about these issues at some stage at least. And let me just end with one thing that, okay, all this, so there's one universality in whatever we have discussed so far, in the sense that the infrared structure has a lot of universality, but there is also there is something else which is universal about quantum gravity, which is the fact that the Hamiltonian is a boundary term. So without even asking hard questions about dynamics, we could ask, just the fact that quantum gravity is holographic in the sense that the states satisfy Wheeler-DeWitt equation. Is there a way that information in the bulk can be encoded in the boundary in a precise sense? And I think this is something Suvrat will talk about. So naively, we see that there is an algebra of observables, for example, for gravity on past or future null infinity. But it can be shown that this algebra actually can be contained in a much smaller neighborhood of spatial infinity, which I've indicated here in the red segment. So it can be shown that quite precisely actually that the complete information about low energy bulk states, like for example even in the center, can be obtained from the algebra of observables here. So this is not a statement about the S matrix, but just about recovery of information. So yeah, with that I just conclude and then hand it over to Jan. And yeah, thanks. Sorry about the disruption in the middle.
Can you allow my iPad to share screen? It's called Jan, I think.
Yeah, I think you should be able to do that. Can you try that?
Okay, thanks, Alok. That was a nice list of various things and issues that should easily fill a discussion session. Since I have not thought too much about flat space holography myself recently, I decided to zoom out and just make a list of higher level things that confuse me and I don't know the answer to, that I would like to list. I found it interesting that a few days ago, I saw the first job advertisement for a faculty position, I think in Vienna, that is in fact looking for someone who's an expert in flat space holography. So apparently this field by itself has now gained such a stature that it merits having separate job, separate faculty searches. That's great news for all the flat space holographers. Presumably a large pool of the potential applicants are present right now. So if you missed the advertisement, you may want to check it out. It's in Vienna. And I'm looking forward to the check from the Vienna people for the free advertisement. So zooming out, I was trying to think what is actually the question that we're trying to answer and what we know and don't know. And it would be great. So my understanding is very incomplete. If people could chime in and help me formulate as precise answers as possible to all these things that I'll be mentioning. It won't be too, I should be done in 10 minutes or so. So I think the question we're trying to answer is that if we look at quantum gravity on asymptotic Minkowski spacetime, so all solutions of spacetimes with particular boundary conditions that have been prescribed, is that by itself dual to something? Does that have an alternative holographic description that I will call F here for flat? And we're asking questions what this F could possibly be. And the first thing that I'm confused about is whether F is in fact a quantum system with a Hilbert space. You would think that a gravitational theory, like thinking about wave functions of the universe and the Wheeler, the width, and so on, should therefore have a Hilbert space, a well-defined Hilbert space, and that F should be a quantum system with a Hilbert space. Like if that's not the answer to this question, then I'm not sure what exactly it is we're looking for. But I wonder what exactly the evidence is that we have that F is a quantum system with a Hilbert space. Because if you look at the perturbative S matrix approach, then that's some states in a Hilbert space that you can define. But whether this can be upgraded to a full duality that really maps the entire quantum gravitational theory in Minkowski spacetime to a quantum system, I don't know. But what I would love to hear from people, how much evidence we have that F is in fact a quantum system with a Hilbert space. And even more precisely, whether F has a Hamiltonian and what that Hamiltonian is. And also, if it has a Hamiltonian, it has time evolution and what the time variable is. So naively, if we think about celestial holography, this on Scribe Plus, the place where this theory lives looks roughly like a null line times a two-sphere. And I think the best possible kind of geometrical formulation of that might be in the context of Newton-Cartan geometry, where we can treat sort of time and space asymmetrically and they don't really talk to each other. But I'd like to know whether F has a Hamiltonian, and if so, what do we know about its Hamiltonian? What's the time coordinate? And does this Hamiltonian have one ground state? Does it have infinitely many ground states because of all the soft hair issues? And is it bounded from below? If it's bounded from below, that would probably be a version of the positive mass theorem for Minkowski spacetime, I imagine. But I don't know for how general a class of spacetimes the positive mass theorem has actually been proven. So I'd love to hear from people exactly what we know and do not know about this. The third question about F is whether F has an operator algebra. What are all these local operators? Is it a complete set of operators? Alok mentioned this feature that if you take two tensors of null infinity, that they seem to commute at different points on the null ray. This could be part of this operator algebra, but do we have a more complete understanding of this operator algebra? Is there a one-to-one map between fields in the bulk and operators on the boundary? What does that map look like? In particular, for massive fields, what is this relation supposed to be? The fourth question I find interesting is, like, does F, this system F, suppose it is a quantum system, does it have a finite temperature partition function? Now, maybe F has a continuous spectrum or an infinitely degenerate ground state, and then this is a ridiculous question to ask. However, we can try to ask this question anyway and see what we learn from it. And so the bulk computation would be how to compute a partition function of hot flat space. Suppose we heat up Minkowski spacetime somehow, what would be the partition function? In Adcft, we compute this using some Euclidean method, right? We just go to Euclidean Adcft and we compute the partition function. That's fairly straightforward. Does any of that have a counterpart for flat space? What would be the relevant Euclidean computation? Are there even Euclidean methods we can use? Can we create states in the theory using Euclidean preparations? Is that the right thing to do? I think it's also interesting if we take this duality to theory F seriously to ask what is the description of a black hole in F. So if F does not have a finite temperature partition function, then what would be the description of a black hole in F? Can it have a temperature? Can it have an entropy? Can we compute those things from F? What would be the interpretation of the temperature of the black hole in theory F, if it's not the temperature of F itself? Is it some other parameter? Is it a very highly fine-tuned set of states in the theory that are difficult to control? How would we even in principle go about studying this? I would also like to understand better whether the gravitational side is well defined. Is in fact, we presumably have to embed everything in a string theory compactification if we believe that string theory is a theory of quantum gravity and there is no intrinsic four-dimensional quantum gravitational theory on flat space. But is the gravitational side really well defined? Are there possibly instabilities in the system as you excite the system? For example, if you have compact internal circles that break supersymmetry, you could have bubble of nothing instabilities. Maybe we can even make bubbles of ADS in flat space that destabilize the thing in certain circumstances. I think the cobordism conjecture of the swampland program might suggest that you can make bubbles of anything. So is the left-hand side, in fact, is that a well-defined set of geometries to work with? Is that in some sense a well-defined closed quantum system by itself? Or is it possibly unstable against decay and all kinds of other geometries of other asymptopia? Is there a Euclidean version? I already mentioned. Can we prepare states with Euclidean methods? Does F have a Euclidean version that we can use? Or is F an intrinsically Lorentzian or otherwise object? And of course, if you're a bit more minimalist, you could say, well, you know, this is not what, this is way too ambitious because all that we're doing is we're doing some elaborate kinematical reorganization of the S matrix of flat space scattering in terms of some group theory. We do some harmonic analysis. It's some 6 J symbols of SL2C and they're cleverly reorganized and there's some spectral representations, but it's all harmonic analysis, blah, blah, blah. Like a minimalist way to look at it. And you might have the same issue with like holography and de Sitter space, where there might be a relation between Wheeler-DeWitt wave functions and correlators, but that does not mean that these correlators are the correlators of a bona fide theory. They might just be kinematical objects. It's a bit like generalized free field theory, where you write down correlators, they obey Ward identities and they're nice, but there's no actual necessarily underlying Hilbert space representation. It need not be a stress tensor, etc. I cannot help but bring up good old BFSS because we did have way back when a different sort of holographic conjecture for quantum gravity in flat space. This is the good old BFSS matrix model. This was supposed to be quantum gravity in 11 dimensions. The matrix model, the quantum mechanical matrix model, was supposed to describe gravity in 11-dimensional flat space. But you cannot apply the BFSS thinking to 4 dimensions. Because, for example, if you compactify M theory, I should say this correctly, on the 7 torus, then if you apply the BFSS thinking, you should get the theory on D7 branes or on 7 branes, and there is no interesting decoupling limit. There's no interesting fixed point in 8 dimensions. That stops in 6 dimensions with the 2-0 theory. So therefore, there was never any interesting field theory candidate dual for 4-dimensional flat space holography from BFSS. Moreover, BFSS, the right interpretation was it was a rather strange corner of gravity in flat space that involved so-called discrete light cone quantization. And I wonder whether those ideas can be applied in 4 dimensions in one way or the other, and whether it does make sense to think about the discrete light cone quantization of 4-dimensional flat space gravity, because in 11 dimensions that did lead to a very nice dual description. But the relation between F and a BFSS type representation is very obscure to me. BFSS in some sense does know about asymptotic states. Because the matrices in BFSS can be decomposed in blocks and you can write down wave functions for the blocks. And in this way, you can sort of write asymptotic states. So there is some hope to connect BFSS, I think, to an F-like picture. but I have no idea how. And I'd love to hear what people think about BFSS and the connection to this version of flat space holography. Alok already mentioned that maybe there's lessons to be learned from Adcft, because ultimately, if you go to a piece of ADS, which is well below the curvature radius, it's approximately flat space. And if we believe we understand quantum gravity in ADS, we apparently also understand quantum gravity in this flat space patch. However, to decouple something there, to have an isolated system that does not interact with the rest of ADS is very difficult. We know how to extract an S matrix, but to actually engineer boundary conditions on the boundary of ADS so that you localize gravity in some cube in the interior, that might be quite difficult. The closest cousin of this procedure might be TT bar deformations, where you sort of move the boundary inward. The TT bar deformations give you a Dirichlet boundary condition, not the type of boundary condition that we want for flat space holography. Moreover, it's typically a time-like boundary and not a null boundary. But maybe there's some contrived version of a TT bar deformation that allows us to bring the boundary in and at the same time engineer boundary conditions so that it starts to be reminiscent of what we want for flat space. But I have no idea if that's feasible or not. In any case, this is clearly a way to embed a lot of the quantum gravitational physics of flat space can clearly be embedded consistently in a larger system. But whether you can truncate a larger system self-consistently to the smaller subsystem is not clear to me. And finally, is there any evidence that all of this requires strings? Was string theory ever relevant for this discussion? You might make the same argument for Adcft, but then with somewhat more elaborate Adcft reasoning, I think you can argue that you do need extended objects for the whole thing to work. And I'm wondering whether there's a counterpart of those types of arguments that would apply to flat space. Or is it something that does not seem to require strings, extended objects whatsoever? It might as well work without all of that. And maybe a minimalistic theory of just Einstein gravity with few matter fields in flat space might have a consistent dual F. And those are my 10 questions. And I'll stop here. Thank you.
Thanks a lot, Jan. So if there is we will of course have a longer discussion, but if there's a quick clarification, then you can ask Jan now. And also you can type in your questions in the chat, which I'm looking at. So. Okay, so maybe we come back to Jan after the other panelists. So go to Anna now.
Sorry, I'm trying to share. Let's see. Okay, can you see? Can you see my screen? Okay, so first of all, thank you very much to the organizers for organizing this interesting conference, and in particular to Alok for inviting me to be on this panel. Today, I thought I'm gonna just focus on one particular aspect of celestial holography, which I have been confused about recently, and which I also think that may have some connections to the topic of the workshop. So I'm not going to spend any time sort of reviewing what we learned from this program recently. So there is Andrea's wonderful talk, which you can watch online to sort of see what the status of the subject is. So instead, actually, let me start by asking, well, one of the big questions which people are wondering about when talking about celestial holography is what we can learn about quantum gravity in asymptotically flat spacetimes from this reformulation. So this is a very big, very ambitious question, and we definitely do not have an answer to it right now. But so Jan had a very interesting list of open questions. So again, I really don't have answers for any of them, but I think what I'm going to be saying today actually relates to his points 3 and 9 in particular. So let's try to focus a bit more, to zoom in a bit more on this question and try to ask, well, we already know that in ADS CFT, there is a well-defined spectrum of the theory and operator algebra. And in particular, one of the remarkable features of conformal field theories, and in particular holography, is the fact that on the one hand, in the CFT, once you are given the spectrum and the 3-point coefficients in the theory, then you are able to essentially reconstruct all of the observables of the conformal field theory. And then by holography, that tells you essentially all you, at least in principle, all you would want to know about a quantum gravity in asymptotically ADS spacetimes. So naturally, one can ask, does this generalize in our case? Does this apply to celestial holography? And of course, again, this is a very, very big question, but perhaps one can zoom in even further and kind of ask whether one can at least have such a description in a particular sector of the celestial conformal field theory in some very special situation, for example. And indeed, there's been some work, and again, Alok very nicely summarized it by Banerjee and collaborators, where it has been shown, or at least there is some evidence that the MHV sector in gravity and gauge theory can be reconstructed from such a philosophy. So the philosophy being that one starts with some spectrum of operators and some operator algebra or some OPE expansion, and then uses that to reconstruct or to build up MHV amplitudes. So that idea, that program is very involved, but it's actually relying on a very simple idea, which is the idea of studying the symmetries of the celestial sphere, so of these celestial theories. And let me just briefly review one example where we know that symmetry actually can tell you can tell us something interesting about the interactions of the theory. So we know that in gravity, there are collinear limits that govern the limit when one takes two massless particles to be parallel or to be collinear, which on the celestial sphere translates into a statement about the OPE. So here I'm in a setup where, for convenience, we're promoting the celestial theory to be Lorentzian. So we're treating Z and Z bar to be real independent variables. And to avoid subtleties, which are well known to kind of govern the subject, we will just fix our Z bar coordinates and take a holomorphic collinear limit where we take Z1 and Z2 to be close to one another. So again, these are the points at which two celestial gravitons are inserted. And I'm just going to focus on the limit where I'm taking two positive helicity gravitons to be close to one another. And in this limit, symmetry arguments, in particular, global conformal symmetry actually completely fixes, just like in conformal field theory, what the right-hand side should be to leading order. So there are corrections here, which are subleading in a collinear expansion. So everything is determined up to some coefficient. So this is what you would call an OPE coefficient in conformal field theory. So here, there is a similar thing, which is a priori not fixed. It's not determined by just kinematics. On the other hand, we know the celestial conformal field theory actually have more symmetries, which are inherited from bulk symmetries, and one of them is translation invariance. So this is a symmetry that relates operators in the celestial theory, as Andrea reviewed, which have shifted dimensions. So if you impose, or if you demand that this OP here is translational invariant, one arrives at a constraint on this leading OP coefficient. And this constraint comes in the form of a recursion relation. Now, this is not sufficient to completely fix this coefficient. However, remarkably, one can go a bit further and invoke these additional symmetries we know to exist, which come from the soft theorems in the bulk. So in particular, if one considers the sub-subleading soft theorem, one arrives at another non-trivial relation, which again takes the form of a recursion relation. So I'm not writing it down here. So this is just the action of this symmetry on a graviton. And so imposing it again as to be a symmetry of this OPE, one arrives at another recursion relation, which together with the first one pretty much completely fix this coefficient. This coefficient takes a very simple form. So the normalization here is fixed by the leading soft theorem. And otherwise, it was shown that it can also be shown by direct computation from a scattering amplitudes point of view and taking Mellon transforms or whatnot, but it can be shown purely from a symmetry point of view to be proportional to this Euler beta function. Okay, so and then in these more recent works, this sort of approach has been generalized to actually understand other terms in this expansion, so subleading ones and so on and so forth. And as I said, they've been kind of exploited as much as possible to reconstruct scattering amplitudes from this point of view. So this provides some evidence that perhaps there is a sense in which there is an operator algebra, which describes at least some sector of something like gravity in asymptotically flat spacetimes. So, but of course, we do not have, a priori, we do not have this full OPE. Now, one can ask, well, is there any way to get a handle on whether there exists an OPE or what this operator algebra is, which actually has as a starting point something we understand a bit better. And indeed, the things which I would say the objects which we understand best as of now in this program are actually the celestial amplitudes as computed by these maps, using these maps from the scattering amplitudes in the bulk. And again, in usual conformal field theory, conversely, 4-point functions, for example, can be used to extract information about OPE coefficients. So one could ask a similar question here, namely if one can use something like a graviton 4-point function to actually infer or extract information about the OPE coefficients in the operator algebra and the spectrum and so on and so forth. Again, it turns out that this question is actually kind of non-trivial, and two of the reasons why it is so is that, so first of all, massless, so here we're interested in massless scattering, so we're just restricting to something like pure gauge theory or pure gravity, and it's known that to all loop orders, in all situations, massless 4-point functions are actually 0, unless the 4 points lie on a line or on a circle on the celestial sphere, or equivalently, this cross ratio on the sphere is real. So this is very weird from a point of view of usual conformal field theory. So we know that most 4-point functions that are typically studied actually factorize into a holomorphic and an anti-holomorphic piece. Well, here we have this delta function which prevents this factorization. So you may think that this is a problem. Then another also pretty head-on obvious problem is the fact that massless 3-point functions are actually singular. They're conformally covariant, as they should be, but they have this delta function singularities. And again, this comes from momentum conservation in the bulk. So, and again, so if you think a little bit about the connection between the OPE and how one reconstructs things like 4-point functions from the OPE, you're going to realize that that argument kind of fails through, because the conformal blocks are typically built out of the usual conformally covariant 3-point structures, which are non-singular, and not out of these very singular ones. Now, nevertheless, one can still well, but there is still, let me just point out that 4-point functions, nevertheless, they are conformally covariant, and they do take the form of a conformally covariant prefactor and the function of the cross ratio, as they would in a conventional conformal field theory, which actually their structure, this kind of global conformal symmetry actually still allows you to ask the question, well, can we write down some conformal block decompositions for these objects? Now, the coefficients, the crucial thing in conformal field theory is that the coefficients of these expansions, if these 4-point functions were honest to God, conformal field theory correlators, then the coefficients is factorized. Of course, this is not guaranteed here, but nevertheless, one can ask, can we do a spectral decomposition of these 4-point functions? And indeed, one can, and just for simplicity, let's just start very simple with just zooming even more to perhaps a problem, which is just a toy model at this point, which is the scattering of 4 massless scalars at 3 level. So from the Boer point of view, the amplitude is very well known. So it takes the form of, it has 3 contributions from S and T and U channels. And the corresponding celestial amplitude can be written down and explicitly computed, and similarly contains 3 terms. And the simplest term you can sort of see from this expansion already, since it takes this form of a prefactor multiplied by a sum of 3 terms. Of course, the simplest looking term in this expansion is the one where we have a 1 here. And this is particularly the term that corresponds to the T-channel exchange. And so indeed, if you start off with this contribution and go through the usual procedure, which allows you to extract the conformal block decomposition from the 4-point functions, essentially relying on a decomposition in terms of a complete orthogonal set of solutions to the conformal Casimir equation, then one arrives at the formula for merely this T-channel contribution in terms of a sum over conformal blocks. And I would say that what's very remarkable about this expansion is not the fact that, okay, yes, we have a discrete series of exchanges at dimension 1 plus n, and we have a continuum of exchanges of dimension 1 and sort of continuous imaginary spin. But what's remarkable, I think, is the fact that these coefficients in these expansions actually factorize. And not only do they factorize, but they actually contain information about these 3-point coefficients. And in particular, the coefficients of these discrete terms factorize into coefficients of 3-point functions involving 2 massless and 1 massive particles on the celestial sphere. So this had again been computed before, and they actually perfectly match, well, up to some subtleties, they essentially perfectly match those 3-point celestial amplitudes. And similarly for the continuum term, the coefficients perfectly match corresponding 3-point coefficients involving 2 external celestial massless scalars and the so-called light ray transform of a massive scalar. So it looks like, at least in this example, things work quite nicely, and perhaps there is a nice interpretation where there is some sort of OPE where one actually has to allow for massive exchanges appearing in these operator product expansions of massless particles. Now, this gets me to the point I wanted to raise, which is that, okay, I focused on one particular term. What about the 2 other terms? So even at 3 level, we have to include all 3 contributions. And indeed, one can play the same game for the other 2 terms. And again, one can write down some conformal block decompositions. So fine, okay, we have now there is a lot more things being exchanged, and perhaps these exchanges resemble some kind of generalized free fields, perhaps in usual conformal field theory. So if you look at sort of the quantum numbers of these things that are being exchanged, they kind of have some similarities to that story. The coefficients, again, they seem like they're factorizing. However, one can find very precise formulas for these coefficients, but now they're not just the usual 3-point or 3-point coefficients that are easily identifiable with 3-point coefficients of celestial 3-point functions of any kind we've computed or we know of so far. So they have this sort of annoying piece, which involves like this generalized hypergeometric function, which, okay, at this point, there is no like really clear intrinsic celestial interpretation for these coefficients. So we don't really understand where this is coming from, okay? So the big question, or maybe the point I wanted to raise is, you know, how do we make sense of these expansions? It's a very simple, concrete question. Is there any way to gain some insight into this sort of structures? Like, how do we reconcile this with some OPE picture, in other words? And to conclude, perhaps what one should be doing is to take a step backwards and kind of, again, as Jan was mentioning, and also Alok kind of pointing to, perhaps one should be thinking about Adcft again, and kind of notice that similar, well, at this point is a very, very vague analogy, but kind of similar structures appear in these discussions of so-called Mellin bootstrap in usual conformal field theories. So this idea that conformal correlation functions have dual descriptions in terms of some kind of Mellin correlators, which it's a very different kind of Mellin transform. So here in the CFT story, one takes Mellin transforms with respect to the conformal invariance on which these correlation functions are functions of. But nevertheless, we know that from very interesting previous work that in the flat space limit, those Mellin correlators actually reduce to flat space amplitudes. And we, from a different point of view, we have a relationship between flat space amplitudes and celestial correlators. So it would be very interesting to understand sort of this other side of the triangle, like of this equivalence, like namely how exactly to get from something like a CFT3 correlator in a flat space limit to a celestial amplitude. And I think that's a question that is very sharp and one can actually work out. And perhaps by taking that kind of point of view or perspective, one can gain some insight into these structures we encounter in celestial conformal field theory, and at least I am very confused about. And similarly, there is this Mellin approach. Mellin bootstrap has also been used in bootstrapping cosmological correlators. So maybe somehow this could be a path in kind of bringing insights from different communities and trying to solve this problem. So this is all I wanted to say. Thank you.
Thanks a lot, Anna. So if there are any quick questions, you can ask Anna now, otherwise we will have a longer discussion.
I have a small question, Anna. You keep mentioning conformal correlators. I thought that in flat space, the relevant symmetry was BMS. So are these BMS correlators or BMS blocks, I mean?
That's a great question. So far we haven't really studied, we just studied these toy models where we just have scalars. So I know that I phrased the question in terms of gravity. At the end of the day, yes, if you looked at the 4-point function of gravitance, you'd expect it to have the full BMS symmetry. But on the celestial sphere, I mean, this work by Shamik and collaborators has addressed some of those questions. But in this problem, I'm just considering the case where we just have scalars, which are not even coupled. They're just coupled to some massive particle. There is no gravity. So these ones we're studying, these ones I've presented, they won't necessarily need to have BMS symmetry. But of course, yes, at the end of the day, that's the problem we're trying to solve.
Yeah.
Okay,
and
yeah, go on. Sorry, yeah.
No, I should say that there is still this big problem that yes, if you try to take this flat space limit approach, as far as I understand, right, like how do you recover from the symmetry? Like how do BMS force symmetries arise from flat space limit? in the usual way by zooming into some middle region of spacetime, as Jan already pointed out, like how do we get the BMS symmetries from this perspective? But here that I sort of try to phrase it more like in a boundary perspective, like not even go through the bulk, but kind of just try to relate CFT3 correlators in a flat space limit to celestial amplitudes and perhaps gain some insight into this symmetry problem from a bulk point of view, but coming from the boundary in some way.
Okay, any other quick questions for Anna? If not, then we will come back after Suvrat. So we have one more panelist. So Suvrat, you can start.
Okay, thanks, Alok. Let me share something. Okay, can you hear me, Alok?
Yeah, I can.
Okay, okay. So thank you very much, first of all, to the organizers and to Alok for putting this panel discussion together. It's a shame this is happening virtually because I've always wanted to go to Prague, but I've never got a chance. So I'll have to wait for the next workshop, which I hope will happen soon. I thought I would just make a few comments about flat space holography. This is not, I'm just going to make a few comments and I'll try and relate to some of the points that were made by the earlier panelists as well. So I thought I would focus on these two questions in the context of flat holography, which I think perhaps deserve more attention than they get. And the two questions are as follows. So the first question is, why should we expect gravity in flat space to be holographic? Why should it even be that we have one example in Adcft, but why should it be that we expect gravity in flat space to be holographic? And the next question is, where should the holographic dual theory of flat space live? I'll try and tell you that I think we have some understanding of the answers, I mean, not a complete understanding. These answers are more interesting than one might think, and I think they might have something to teach us about how we should approach this problem of flat holography. So these are the two questions that frame the talk. But the way I thought I would approach these questions, and of course this is up for discussion, we should have more discussion on this, is that I thought I would say a little bit about what lessons Adcft teaches us about these questions, because that's something that we understand very well. We've understood it now for 25 years. So I thought I would say a little bit about ADS and then say a little bit about flat holography itself. So let me just go back to ADS and say say a little bit about these perspectives. So the first point I'd like to make about Adcft, and I guess this is also related to what the earlier panelist said, what Anna said, is that in ADS we can of course do something similar to what we do in flat space holography, and in fact much of the recent literature on flat holography is motivated by this program in ADS, which is how Adcft was first explored, which is the fact that we look at S-matrix elements in ADS. And then when we look at S-matrix elements in ADS, we can take a certain extrapolate limit of those S-matrix elements. You set off some ADS excited, you look at correlation functions in ADS, you take these correlators to the boundary. If you scale them up in the right way, you get some boundary limits, and these boundary limits can be interpreted as CFT correlators. And there is a lot of very nice structure in this whole story. One can see the symmetries, the conformal symmetries in these boundary correlators. One can, in fact, also take a flat space limit. So there are two well-known flat space limits. One limit is, of course, in Mellin space. Another limit is in momentum space, where one looks at the sum of mod of ki going to 0. And one can do that with these correlation functions on the right-hand side. One can get back S-matrix elements. One can look at symmetries. One can look at how the 3-point and 4-point functions are constrained and so on. And there's a very nice story that goes along with that. But in a deep sense, I think that this is not really holography. And the reason this is not really holography is that this whole story, this entire story, would work entirely without gravity. We never need to say anything about gravity. You could just take some quantum field theory on ADS and you could do this procedure and you get some boundary correlators. And that's, I guess, related to what Jan was saying in his presentation. which is that, we don't really want to do harmonic analysis. So I think that the really interesting aspect of ADS-CFT is a little more subtle. It's the fact that gravity gives you a little bit more, or actually much more, than just the fact that you can rewrite some ADS scattering amplitudes as some correlation functions. It's the fact that, in fact, the information about the entire state does not require us to specify correlators on the boundary at all times, but rather the CFT state is determined at a single instant of time. So what holography really is telling us is that information in the bulk is stored holographically, in that if I give you correlation functions for a single instant of time, then that is already enough to fix the entire state. And this is a property that is uniquely gravitational. It's simply not true that you could play the other game, with a scalar field theory. You could look at some boundary limits of S matrix elements, but it would not be true that information about a scalar field in ADS is determined by the boundary values of the scalar field at that instant of time. But it is true for a gravitational theory, and this is in some sense, I think, the deepest statement that comes out of holography, that the information is encoded at a single instant on the boundary. And there's one more point I want to make about this, which is something we learn in ADS, and it's related to another point that Jan made about the Hamiltonian that we expect in flat space. So let me just make an obvious observation in ADS, and I'll return to this again in flat space. It is the fact that CFT correlators at any instant of time have full information about the bulk. So I could give you CFT correlators at this instant of time, or at a later instant, or at an earlier instant, or anywhere. I just need to give you CFT correlators at one instant of time on the entire boundary, and that has all information about the bulk. So I think this is the aspect that really requires gravity, and this is one of the things that we learn from ADS-CFT, which we should apply to the flat space theory as well. Now, I think one of the things that we've learned in the past 2 years is the following: is that the fact that gravity has this property of being holographic is something that, of course, we learned first from ADS-CFT, but it can be shown independently from the gravitational theory. And in fact, the argument to show it is very simple. I won't go through it in detail, but let me just sketch it for you and we can have more discussions. It is the fact that if you look at ADS, one can show that, if you look at the operator algebra on this instant of time, one can show that any state in the theory can be created by the action of this operator algebra on the vacuum. And in fact, that is a property that also holds in the non-gravitational theory. So this first step is a non-gravitational step. It's like what I said earlier. There's a non-gravitational aspect of ADS-CFT, and this first step is that. But there's a second step, which is the realization that gravity has a unique property in that the projector on the vacuum is also an operator at the boundary. And that's a very unique property. If you think of it, in no other theory is it the case that you can project on the vacuum from the boundary at a single instant of time. And that relies on the fact that the Hamiltonian in a theory of gravity is a boundary term. And if you combine these two simple observations, you'll see that if you think of any operator in the theory that takes you from one state to another state, so just get M, ra n, you can, of course, using step one, write this operator as the action of some boundary operators on the vacuum. And this would be true in the non-gravitational theory. But because the projector on the vacuum is also a boundary operator, you see that the whole expression has an element, has an expansion as a boundary operator. And you can do this, since you can do this for an arbitrary bra and arbitrary ket, you can just do this for any linear combination of those as well. And this tells you why the algebra in the bulk is encoded in the boundary algebra at a single instant of time. And it relies very crucially on this projector on the vacuum being part of the boundary algebra, which is a property of gravity. So I think this is one of the lessons that we get from ADS-CFT, which we should apply to flat holography, which I'll now discuss briefly. But there is a general slogan, I think, and ADS-CFT is a specific example of that. And the general slogan is that, if one thinks from a quantum information point of view, then gravity is very unusual in that the information that is present in the bulk of a Cauchy slice, you might have some qubits or some excitations and so on, is also available near its boundary. And this is a unique aspect of gravity, and I think at least that this is the absolutely key aspect of holography, or this is one of the key lessons that comes out of ADS-CFT. Okay, so what does this have to do with, with flat holography or the topic of our discussion? I think it has important lessons for how we should think about flat holography. And I think that, of course, in flat space, we've made progress. It has also been covered in many talks, and also, a very, very nice progress and very elegant progress in rewriting S-matrix elements in nice ways. And this is indeed, what led to a lot of progress in the early days of ADS-CFT. But I think perhaps not enough attention has been paid to the fact that, we need gravity for something to be holographic. Non-gravitational theories are not holographic, even if their S-matrix elements can be rewritten in nice ways. And I think perhaps also not enough attention has been paid to the question of where the information on the boundary resides. In fact, this was one of the questions that Jan had. And I think there is some answer that one can give to this question. So it turns out, and this is, as Alok mentioned, in fact, this joint work with Alok and Siddharth and Pushkala, all three of them are teachers. As Alok mentioned, it turns out one can in fact use the same techniques that I described in ADS, and I don't have time to go through them in detail, but one can show that at least if one looks at massless particles, which are what you would get on Scry plus or on Scry minus, that all information about massless particles that you would have thought required the operator algebra on all of null infinity, in fact is present already near the past boundary of future null infinity. So if you look at the operator algebra on this entire null infinity slice, you can in fact reduce it to an operator algebra in this little red region, and that is a unique property of gravity. There's a similar property that holds at past null infinity, which is that if you look at the operator algebra on past null infinity, you can reduce it to the operator algebra on the future boundary of past null infinity. That's this little orange region here, and this is how this would look like in one higher dimension. Of course, this is an interesting statement about information, but it doesn't tell us much about dynamics because, as you all know very well, in flat space, there's one Fock space one can define at Scry plus, and another Fock space one can define at Scry minus. And these Fock spaces are a priori independent, and in fact, all the interesting dynamics is in the overlap between these two Fock spaces, which is what the S matrix is. So there's this interesting information theoretic statement, which is that if you look at the Fock space at Scry plus, all its information is encoded here, which is a uniquely gravitational property. If you look at the Fock space at Scry minus, all its information is encoded here as future boundary, which is a uniquely gravitational property. And of course, there is an interesting question, which is what's the map between them, which would tell us about the S matrix, to which we don't know the answer. I should say that this is a little different from the proposal that Boer and Suvrat made in 2003, which really started off this program of flat holography. And what they conjectured was that the information is present on the union of the celestial sphere at u equal to 0 and v equal to 0. That would be the middle of Scry plus and the middle of Scry minus. So this is different, but in fact, it's not in contradiction because, we're saying the information is present here on this celestial sphere near the past boundary or on this celestial sphere near the future boundary. But maybe the same information is present near the union of these celestial spheres in the middle of null infinity, and it would be very interesting to understand how that works. But in particular, so this I already said that this result follows from the constraints of the theory. It's something one can establish from the theory of gravity. I should say also in relation to one of the questions that Jan had, it could very well be that strings are required for the theory of gravity to make sense, because maybe string theory is required for the UV theory to make sense. But I think just to argue that the theory is holographic, I think that does not require string theory. I think the fact that the theory is holographic follows from a careful analysis of the constraints. But it might well be, and as we see in ADS-CFT, that there are other reasons that one is forced to include string theory. And that's the only way we know how to make the S matrix consistent. And so, but I think the fact that holography is should be like unitarity in gravity, some property that emerges directly from the constraints of the theory the moment one puts it. Let me say one more thing about this picture. There's an important difference between the way we think about and this will be important in a minute. There's an important difference in the way we think about the boundary of ADS and the way we think about the boundary of flat space. And that is that, if you think about the boundary of ADS, it's really a time-like boundary. Whereas the boundary of ADS, in a sense, you can think of as the limit of Cauchy slices that you're pushing up. So this result I just outlined is telling you holography, that it's telling you if you think of this limit of Cauchy slices as you push them up, so that you get to scribe plus, all that information is available near the boundary of the Cauchy slice, which is this red region here. And so that's a little different from the way things work in ADS. But remember, I said that the information was available at one time and also at another time. In fact, it turns out that in ADS, that in flat space, that is not true. And this is, I think, something that's interesting. It's related to this question that Jan asked about whether there's a Hamiltonian. One can show that, in fact, the information that's available near the pass boundary of scribe plus is not available at a later cut of scribe plus. Rather, you progressively lose information. So let me just say something about future infinity, future null infinity. There's an analogous statement for past null infinity. One can show that you lose information as you go up along future null infinity. So this first cut has a lot of information. It has all the information about all of scribe plus. The second cut has less information than this first cut, but it does have information about everything to its future. This third cut has less information than the first two cuts, but it again has information about everything to its future. So in scribe plus, a cut has information about everything to its future, but not to its past. And the converse is true on scribe minus. And this has to do with the fact that conventionally we study flat space with very different boundary conditions than ADS, because we allow radiation to leak out, and with radiation, information goes out. And so all the information is available at the beginning, but it's not available as you go forward. And I think that's something that's an interesting aspect of flat space holography, which is different from ADS. Okay, let me just say a few words about massive particles, since that was already discussed, and I'll stop after that. So I think that we've discussed, and there's a lot of discussion of massive particles in the celestial sphere. But the question is, where does this celestial sphere in which we are describing massive particles live? In fact, massive particles, conventionally go from past time like infinity to future time like infinity. And we don't study, we can't study them on scribe plus, since, as Alok already mentioned, or on scribe minus, there is no good extrapolate dictionary for massive particles. So one can take an S matrix, and one can, of course, transform it to make it look like a quantity in a celestial sphere. But where does the celestial sphere live? And perhaps I think the right way is to think of the celestial sphere at living at the blow up of spatial infinity. As Alok already mentioned, this was explored by Jan and Rolf and others in the past. And I think this would be interesting from the point of view of holography, because it would tell us that all the information is available. As I said, information about massless particles is available near this pass boundary of scribe plus, this red region. And then information about massive particles is available on the blow up of spatial infinity, which is somewhere here. So I think that's something that we should take seriously, and we should work into our understanding of the dynamics. So just to conclude, I think the points that I wanted to make, I think that, there is, to answer also partially some of the questions that I raised in the beginning, I think there is a good reason to believe that gravity in asymptotically flat space should be holographic. And I think this comes from general arguments that the constraints force gravitational theories to be holographic, but they do not force non-gravitational theories to be holographic. I think we do have an understanding of some of the information theoretic properties of this mutative dual, which is that information about massless particles, at least, should live near the past boundary of scribe plus or the future boundary of scribe minus. But there's an interesting difference with ADS, which is that it's not true that information lives at any cut. As you move in the future on scribe plus, you lose information. So there's something specific about the past boundary of scribe plus or the future boundary of scribe minus. And this suggests a location for the dual theory. And if we do want to write down a dual theory on all of scribe plus, this dual theory must somehow lose information. It can't evolve unitarily on scribe plus. So I think these hints should be taken seriously in looking for the dual dynamics. And as I said, I think a lot of progress has been made in understanding how S matrix elements should be rewritten as CFT correlators. But I think we should also try and understand where the CFT really lives, where the extrapolate dictionary is. And I think these are some hints that tell us about how that should work. And as I said, in this picture about information theoretic arguments, there is little we can say about the dynamics, and it would be nice if somehow we could combine this with insights from S matrices and say more about the dynamics. So I think these are questions that hopefully will occupy us for the rest of this panel discussion. So I will stop here.
Thanks a lot, Suvrat. So, is there any quick question for Suvrat?
Can I ask a question? I mean, I can also wait for later. I'm not sure if it's a quick one. Should I go ahead or?
If it's a longer one, maybe we can just do it.
Yeah. Okay. Maybe let's wait.
Okay. Yeah.
Quick.
So if there's no quick question, I mean, first we should just thank all the three panelists for giving us really complimentary perspective on the problem. Now Anna, you can ask and maybe we can merge into a longer discussion.
Yeah, so I have a question for Suvrat, and I think it's something it's my confusion, and perhaps maybe you can help clarify it. I've been a bit confused about the statement that all the information is contained at the pass, for example, pass boundary of Scri plus, in a situation where one allows for something like a shock wave or like some, like in the situation where you have the memory effect, where we know that there is a vacuum transition between like Scri plus minus and Scri plus plus. Like in some sense, isn't there a sense in which like an observer at Scri plus minus wouldn't know about like this induced vacuum transition that would have happened after the passage of some?
I think this thing that you mentioned is not that hard to answer. I mean, so there's one question about the vacuum transition, but we could also just look at an energetic shock wave. So that's perhaps the simplest kind of question one can ask. Maybe let me see if there's a whiteboard. I mean, anyone can write in this whiteboard. Maybe it's for discussion. Why can't I annotate this? Is there some setting that we need to change that only host can annotate or something? Can you? There's one more Suvrat. If you could make that a host, that would be useful. I think maybe only hosts are allowed to annotate or something, which is the iPad that I have. In the meantime, I'll just try and do what I can with the mouse. So we could ask a simpler. You could ask the following. The following question, right? We could take a shock wave here that comes and hits the boundary, and let's say there's an observer here. So how does this observer even know about the shock wave that's coming to hit the boundary? Would that be a fair representation of your question?
Yes, exactly. I'm confused about, like it seems like it's Scri plus, then you would,
No, but I think you would, because the point is you need to measure the correlation function of the Bondi mass here, and also the matter field that makes up the shock wave. So if the shock wave is made of some matter field, you can measure the Bondi mass and the limit of this as you go to Scri plus minus and this phi. So you can check that if the shock wave, for instance, was of this form, f of x, it is not equals to the other one. Okay, let me see what I can do with the mass. If it's of this, so it's a shock wave that's centered here. If it's a shock wave of this form, then you can check that this correlator, if you compute it in this state, has the following form. But this U is this insertion I made here. So notice that this correlator, so this is a correlator, but in a non-gravitational theory, this would just have vanished, because the reason I took this form is because this is a unitary operator. So the correlator I'm computing is like U dagger of some operator and Scri plus minus and U. And in non-gravitational theory, the unitary would just commute through this operator and you just get the vacuum answer for the correlator. But in gravity, because of the presence of the Bondi mass, you get some non-zero answer. That answer is this, if I remember correctly. And this integral over x goes from 0 to 1, but this answer has support at u goes to minus infinity as well. And in fact, you can check if you know this answer, you can determine completely the function f of x. Now you could ask questions about more complicated shock waves and so on, and you need to measure higher and higher point correlators, but you can always get that information. So it's the fact that there is a Gauss constraint in Scri plus, even though we usually forget about it because in asymptotic quantization, it's so it's so simple. You specify the news, and then you can just solve for the Bondi mass using the Gauss constraint. But the Gauss constraint is really there, and that's what forces information to be near the pass boundary. In this example, this is the answer. In this 2-point function, will give you the answer. I don't know if that's clear. we must have something like this. Somehow this has to be, otherwise the theory would not be holographic. It must be that information is, if information is present only on scribe class, that would be true even without gravity. But information is always present in all of scribe class. So what's special about that? It's the fact that information is present every in scribe plus minus. But this is the specific answer to the question.
I see. Thanks. I need to think. I'll think a bit.
Okay.
On that. But that was very helpful. Thank you.
Okay. Thanks.
Any other questions?
It looks like Alex got his hand raised.
Alex, yeah, please.
Yeah, thanks for all the panelists for the really nice presentations. So I have two questions about taking the flat space limit of ADS. The first question is whether this is supposed to work at the non-perturbative level. So if I give you, a 4-point function in n equals to 4 or ABJM, finite n, finite lambda, as a function of the cross ratio, can you extract from that a non-perturbative flat space S matrix? And the second question is related to the internal manifold, because when you take the flat space limit of that correlator in n equals to 4 or ABJM, typically you kind of, because the internal manifold is ADS scale and you zoom in, basically what you recover from that is a 10-dimensional or 11-dimensional supergravity S matrix. And so, well, okay, I don't have a very sharp question, but trying to look for holography directly in flat space holography directly in 4 dimensions may work differently than if you have to go to the full 10 or 11D. Okay, so those are two sort of open comments questions. If anybody wants to say something, that would be great.
I think that's a really good point. Sorry, can I say something?
Yeah.
Yeah, I think that's a really good point, Alex. I think so. Let me say, please correct me if I'm wrong. I think we don't have a good non-perturbative understanding of these limits. The way these limits work, so there's one limit we understand well in Leonard space and momentum space. And the way these limits work is one looks at perturbation theory in ADS for Witten diagrams, and then one takes a limit and one can show that reduces to perturbation theory for in that space, if you take the right limit. But if you want a non-perturbative answer, what you want to do is you want to keep G string finite. But if you keep G string finite, you're keeping G angle squared finite, and then you're out of the Toft limit. So everything we study ADS CFT often in the Toft limit, right? You keep G squared n finite, but take n to infinity. But here, if you really want to study like how things would be like in a non-perturbative sense in flat space, you'd want to keep G string finite and take n to infinity, and then you're out of the Toft limit. And so I don't think we have an understanding of that. And I think that's why it's quite hard to understand flat holography starting with the flat space limit of ADS. If you study ADS in the Toft limit.
Yeah, so this, I think Panathonis and Okuda's paper was exactly out of the Toft limit, right? They take large n and keep G Young-Mills fixed. So, Toft coupling diverges, and they showed that the reduced amplitude, they look at two scattering of like stable string states like dilettantes, and they showed that it was coming from this particular limit of the dual theory where you take large n and G Young-Mills fixed. So I don't know.
If we say something precise about this limit, I mean, in the other, if you're looking at perturbative S matrix elements in ADS in the Toft limit, we can say something pretty precise, right? We can extract like S matrix elements from ADS Witten diagrams. But I don't know what control we have. I don't know. Maybe
I mean, so I thought the bulk computation was this dilettante scattering computation in string theory and perturbative string theory, and then it was reproduced by connected correlators in this weird limit where you take large n, where you take G and this. I'm sure many people know more than me about this, so they can say more.
But sorry, Suvrat, you can study effects even if you're in the Toft limit. You can study effects that. Finite n is maybe not the right way to talk about them, but like when we talk about black hole states, we can probe black hole states in the Toft limit, even though the black hole states have energy of order n squared, which you might think is infinity if you literally take n to infinity, right? So I mean, we can talk about n is, I don't know, 10 billion, and then we just make lambda 10 million, right? Maybe that's not the literal TOEFL limit, but it's close enough to it that I think that should make sense, right?
So maybe I didn't understand. Is this related to Jan's question? So we want to take the ADS scale to, to 0 compared to blank scale, ADS scale to infinity, length scale to infinity compared to blank scale. But we want to keep G string finite. So we somehow, because we want to see string theoretic effects that would happen in flat space. So we need to take like lambda to infinity, which we keep G string. I mean, so I don't understand how does.
No, lambda goes to infinity, I think, in that. Yeah, right, you're right.
If lambda goes to infinity, right? So then we're out of the TOEFL limit. I mean, otherwise, we always, if lambda is finite, we always seeing the effects of ADS, right? If you want to get rid of the effects of ADS, we have to take lambda to infinity. So aren't we forced to go outside the TOEFL limit?
I think yeah. I mean, I think that was Penedones and Popoda showed in their explicit computation.
Yeah, sorry, that's something that maybe someone else should
yeah, maybe Jan or someone else can comment.
I think the other issue that you seem to zoom in on 10-dimensional flat space rather than 4 or 5-dimensional flat space is also interesting, because there seems to be a fundamental problem embedding any flat space solution, including, say, a Calabi-Yau or some other internal manifold into an ADS context. And if you want to do that, you need an infinite family of ADS solutions where there's a hierarchy between the curvature scale of the internal manifold and the ADS curvature scale. And I think we kind of believe that maybe there's a bound on that hierarchy and that you cannot tune the ratio of those two length scales arbitrarily. And if you cannot, then there's a fundamental, I don't know what the status of that conjecture is. Because if you could tune it arbitrarily, then I think you could make the Sitter vacuum of small uplifts, blah, blah, blah. But then there might be a fundamental obstruction to embedding flat space solutions in ADS. And maybe that means something. I don't know what it means.
Any other questions? Tarek has his hand up.
My hand is raised, but slightly orthogonal to what we were discussing. So if there are other questions along the same lines, we can let those happen first.
I think you're the only hand which is raised right now. So.
Okay.
Yeah.
Yeah, so my question is somewhat along the lines of a point that was raised by Jan in his slides about what is the role of BFSS. So one thing I think that's interesting is that anytime that we get some S-matrix like picture in like holography from the top down rather than from the ground up, it always involves matrices, and then in a sense not just one radial direction emerges, but like all of them. Like you start with just matrices, matrix quantum mechanics and time, and then all of a sudden you get an S matrix. That S matrix can be the S matrix of some other theory, like BFSS, it's 10D flat space or 11D. Or in the C equals 1 model, it's some linear dilettante solution that's not quite flat space, but it has an asymptotic region. But somehow, all the data of the space-time is encoded not in a field theory, but in some other structure. So I was wondering, for all the people who study BMS and all that, is there an understanding of how that BMS symmetry would be realized in such a model? Or, like, is there anybody thinking about that?
There may be a simpler version of this question in the C equal 1 model, where you can actually compute the S matrix, and it has some W infinity symmetry. I don't know if it's a simplified version of this.
Yeah. Also, in some sense, BMS is a very 4-dimensional. So we don't know if there will be something like BMS in the 10D case.
Well, right, but yeah, the question is, okay, say you have the 10D analog. Like, for example, in the C equals 1 case, it's W infinity. The 10D case, it might be something different. Maybe that's a place to start, and then see how that symmetry acts on, the building blocks of the matrix model, for example. Like, is there a picture for that? Like it might act on the S matrix in some way, but do we have an understanding of how it acts on the fundamental degrees of freedom?
But the symmetry itself might be approximate or emergent, right? So it might be a very difficult question from the underlying theory.
But you see, if it is emergent, like you say, then it seems kind of strange to then structure all our searches on this symmetry. You know, like.
Well, it's something you want to land on, but
yeah, at the end, yeah.
Yeah. But you better know what it is that you want to land on. And perhaps structuring it in one language versus another might be easier to identify what you want to land on.
So is it known how to structure a matrix model such that you land on the W infinity symmetry, for example?
I mean, the only S matrix I know that pops out of a matrix model that is very explicitly discussed is this Fermi C picture. I'm not sure of any other example. Maybe someone else knows.
So sorry, in BFSS, isn't the common wisdom that the flat space is the moduli space, vacuum moduli space of the theory, basically?
Well, BFS has some flat directions, and you can imagine scattering the zero branes themselves in terms of some asymptotic states, but I'm not sure how much of that can be computed in a controlled way. And
well, maybe, yeah, but as you say, maybe it's not impossible to find a super translation type thing in BFSS. It's, I mean,
so asymptotic, yeah, sorry.
Yeah, it's a property of asymptotic states. It's a better reminiscent if you write like a worldsheet string theory in ADS3 and you ask how does the worldsheet theory see the Virasor algebra at the boundary. It's actually somewhat not straightforward. You need to identify weird vertex operators and so on. And so I would imagine that for super translations in BFSS, maybe something similar happens and strange operator, but maybe it can be done.
But in 10D, we may not have super translations even. I mean,
we don't know, but you explore it at least, right?
Yeah, yeah.
I had a question for all the panelists. I don't know if there's, I guess it's regarding the nature of the underlying degrees of freedom. So there are some thoughts experiments that you can do in ADS where you consider a large ADS black hole and take its radius to approach the boundary of ADS. And this allows you to estimate that the number of degrees of freedom has a parameter n squared, for example, in the case of ADS 5 times is 5 times the volume of the boundary. And this is a very suggestive depiction of the underlying degrees of freedom of the dual CFT that suggests it's a local quantum field theory that at each spatial point has n squared degrees of freedom. But crucial for that was that the parameter n was still encoded somehow in the bulk theory. There was this n, which was the ratio of ADS to Planck to some power. In flat space, somehow we lose this kind of thought experiment. It has to do with the underlying UV degrees of freedom and the question of Jan about finite temperature, in a sense, because if we try to mimic this experiment, we put a big hole, black hole in flat space and it becomes very cold. And it's not clear that this is the natural excitation of all of the degrees of freedom. It's something else. And then there's this missing parameter, which is LADS over L Planck or L de Sitter over L Planck even, which somehow is not part of the story. In string theory, there is still a dimensionless number, which is L string over L Planck. But I don't know if this is counting the underlying degrees of freedom. So I wanted to ask the panelists if they had any remarks about hints or this type of Gedanken experiment that could illuminate a little the underlying degrees of freedom using just the low energy description of the theory.
So one conjecture I think Raman Sundaram had was that, because there's an IR divergence in flat space. So, you have to put an IR cutoff and that could act as a,
in ADS also, you could say there's we put a little cutoff near the boundary and that gives us some piece of the degrees of freedom that they scale like the boundary volume.
Yeah. So LADS could be replaced by some kind of IR scale which regulates your S matrix. I mean, I'm saying that there was some there was some, 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 there these experiments, Gedanken experiments. But I don't know, someone else can. This is tied to the fact that how to define asymptotic states which give you infrared finite amplitudes also. Is there some built-in cutoff? Yeah, Suvrat, go on, sorry.
No, go on.
No, that's all.
Totally speculative. Yeah. It may be that
I would like to encourage Suvrat to speculate now.
It may be that so black holes, of course, are very different for the reason you said, right? In ADS, they're typical states, big black holes. But in flat space, we don't even have an understanding of what a black hole is. Like if I give you some Fock space at psi plus some state, like how do you know it was a black hole or not? We don't know, right? These are extremely atypical states because the entropy of Hawking radiation is small. So maybe this is not the right way to answer the question. On the other hand, in ADS, we do have another promising way which would have led to the same answer about the degrees of freedom. And that would be to impose the bootstrap. And then we would learn that, you have to have a stress tensor, you'd have to have a central charge. And then, you use modular invariance and you find something about the number of degrees. So that's an entirely low energy thing. Like I could do it just by studying like correlators of generalized free fields, and then and applying various consistency conditions. Of course, what I'm saying now comes with a lot of hindsight, but one could have done that. And that is a procedure that clearly can be done in that space as well, right? Because the fact that you have locality, I mean, as I was saying, maybe it's harder because you have these delta functions and so on, but you do have locality on psi plus. The asymptotic theory is local, and just the way you do an ADS. And so you could try and impose, some bootstrap kind of conditions and then impose something more to learn something about the degrees of freedom. Maybe looking at a big black hole is not the right way to go.
If you look at higher derivative terms in the effective action, they also come with length scales. And in string theory, we might think that this is one place where we find the string length rather than the Planck length. So maybe there's a hope to extract some extra parameters from the full effective action rather than just Einstein gravity. Because you could say the cosmological constant is just the first term in some effective action and it sort of sets the leading scale. But if that's absent, maybe we should go one term higher and use that as our extra scale and our n somehow.
So maybe the degrees of freedom is 1 over G string or something to some power, you mean?
Possibly, or well, it could just be 3 level, but the string loops, I don't know. Yeah, I don't know if that's a reasonable. That's where the hierarchy between scales comes in. If you don't have the cosmological constant. So, but how you would see that show up in black hole entropy, then you would need to take that, and then it becomes obviously peculiar. But maybe objects, maybe the more interesting things is objects that are not semi-classical, but somehow are a balancing act between the first and the second term in the action, because that's precisely where we get the n scaling from in Adcft. So maybe we should look at small black holes with high curvature that sort of balance those guys, and maybe there's a regime there that has a different specific heat, and maybe those are more fun things to explore the density of states. It will be free to completely bullshit, right, today, so it's fine.
Just one more thing. Of course, in Adcft, we haven't had much success in understanding small black holes either. I mean, we understood. So, if I were to ask what is a small black hole state, we don't even know what that is. In fact, it's an atypical state in the Hilbert space and ask you to identify its flux. And that's as hard a question as understanding what a black hole state is. Right?
I have a question for Suvrat. So you made the point, which is very much based on the Hamiltonian constraint of GR, that the information is localized in a tiny epsilon size null interval times spherical information, basically. I guess it's encoded in some infinite list of one-point functions of arbitrary operators that live sort of over there. What's your idea about the inner product as defined? So you were referring to information that's available at the boundary, but we would, yeah, and apparently it's enough to reconstruct the state. Can we also construct the inner product at the boundary?
You mean the inner product between scribe plus and scribe minus, right? Because the inner product at scribe plus is trivial. So that we know from asymptotic quantization. That's just a Fock space. But
between in and out state.
Yeah, between in and out state. So that's the one between scribe plus and scribe minus. So that we don't have much to say about. I mean, that's a very interesting question. I mean, in some sense, the result we have is kind of in an out formalism. You define the state in scribe plus and you detect it in scribe plus. Or you define it in scribe minus and you detect it in, you know, so you can define it in all of scribe plus and you can detect it from a small interval of scribe plus. And vice versa on scribe minus. But now you could ask, which I think is what you're asking is, I define a state in scribe minus and now predict the form of the state in scribe plus. That's the S matrix. So that we don't have much to say about, although that's clearly the most interesting question. I mean, if we did, then we would have a much better understanding of that. That's the dynamical question.
Can I ask a quick follow-up?
Yes, yes.
So does the antipodal matching condition play a role in your construction, or are you really just looking at either scribe minus and scribe plus and talking about them individually?
Yeah, really only scribe minus and scribe plus. So even the fact that the super translation charges are conserved between scribe plus and scribe minus, it's not important because we're defining a state on scribe plus in the scribe plus Fock space and just saying it can be identified from the transform. And so in some sense that's, yeah, it's quite different from ADS, right? We have these two different Fock spaces. There's an ADS, you know, we have one. There isn't any naturally. There are two different spaces. So there's something different, and you're right. The dynamical question is all about the mapping between those two. And so that's what a theory of a flat dual theory should tell us, right? That is the job of the dynamical theory. It should be to tell us what the mapping between scribe minus and scribe plus is. Reconstruct the S matrix.
I'm then just a bit confused if you say that all the information is either in the future of the past boundary or the past of the future boundary, and anything dynamical going on in the space-time will require that that notion of matching.
So anything dynamical will require it, but you see, I can say that if you did so you could define a Fock space in scribe plus. That's just a Fock space, and you could define a state in that Fock space. And then the claim is you can identify that state uniquely from the past boundary of scribe plus. But the description I'll get for that state will be in terms of the Fock space at scribe plus. Alternatively, I could define the state at scribe minus in that Fock space, and I could identify it uniquely from the future boundary of scribe minus. But this question is not interesting. I mean, this answers some information theoretic thing, but this is not useful for answering the question of I define a state in scribe minus and tell me the description in scribe plus. So it's like an in-in formalism or an out-out formalism. What we want is an in-out answer, which we don't have.
So Alex has hand up.
Yeah, I also wanted to ask Suvrat a question about localizing information and whether strings are needed or not. So what happens to this picture of localizing information near the boundary if you start adding alpha prime corrections to the effective action? Then, you know, the Wille-DeWitt equation or the nature of the constraints can be very different. You may even have, you know, more than 2 time derivatives in your low energy effective action. Do we still think that everything remains holographic at arbitrary order in alpha prime, or how do you think about that?
I think so, because all we need is that the vacuum can be identified from the past boundary of scribe plus. So if you go asymptotically far away, and you know, if you can use some operator which might be a generalization of the ADM Hamiltonian to identify the low energy vacuum, then that is sufficient for what we're saying. I mean, and this is true in ADS as well, right? You go asymptotically far away. In ADS, there could be a lot of things happening in the bulk, but you go near the boundary and you believe you have a good understanding of the vacuum term, and you can identify the vacuum from the asymptotic Hamiltonian. This is, so you know, so a lot of these alpha prime corrections and so on are presumably important, and they're important in the bulk where all sorts of things are happening. But what we need is just the fact that, you know, there is an operator near the past boundary of scribe plus, which can be used to identify the vacuum. I think if such an operator didn't exist, then the theory would not be holographic. I mean, it could be that such an operator doesn't exist in full theory. But if it didn't exist, then I think the theory would not be holographic.
And is there no additional subtlety in flat space compared to ADS? Because at the same time, at the same order at which you'll see these higher derivative corrections, you're also going to have massive particles that you can view as having integrating them out gives you these higher derivative corrections. You can probably view it in two different ways, but the massive particles somehow, you said, might live at a very different place.
Yeah, so massive particles is one subtlety, as you said, and I think the right way to extend this should somehow be to understand massive particles as the blow up of spatial infinity. I think the way we currently understand massive particles living at I plus or I minus is clearly not the right way to understand this for holography, because then these would be something that would be out of the scheme of holography, right? They're living at a very different places. If you could understand them well at blow up of spatial infinity, then I think that would help with holography. So you're right. We need a different understanding of how to describe massive particles.
Same.
More questions or comments?
Maybe just a quick comment to Jan's question number 10 about the need for strings. So I think generically most celestial amplitudes will not be finite because of the scaling with the energy. And so, for example, even the classical 3-level 4 graviton amplitude, like let's say MHV 4 graviton amplitude, is divergent and can be softened when you consider string theory. So I think there's an important place for string theory or another UV completion of quantum gravity there to make even these basic objects well defined.
Right.
Does that, how much just finiteness, does that limit sort of the UV completion of gravity in any way if you just insist on finiteness?
Sorry, what do you mean?
Well, you have these divergent graviton amplitudes that I guess at high energy strings makes the scattering softer, and when it's
exactly
you just go backwards and you just demand finiteness. Do you get the softness of string theory, or is that constraint much weaker?
You mean whether the string theory is the unique UV completion that makes these objects consistent?
Well, is the softness that string theory gives to high energy scattering amplitudes, is that necessary to get finite amplitudes, or could you get away with something that's not as soft as string theory but still?
Yeah, so that's asking whether that's the unique way to make them well defined, and I don't know the general answer to that. In the cases where it has been looked at,
but there may be
it seems like you need the softness.
Yeah, there may be other constraints like causality, right? So that may, like Maldassen and Gibaud, those constraints. So that may tell you that the other mechanisms which make soften UV behavior may not give you causal theories. So that could be. Any other questions?
Maybe, I have a comment related to the point. So if you just look at 4-point scattering, right, there is this idea, Andrea already sort of reviewed it, that everything about like scattering in asymptotically flat spacetimes is encoded in the analytic structure as a function of this parameter that is dual to the center of mass energy, which turns out to be the sum of the external dimensions. And so perhaps one natural thing to do is to study better and understand like what this analytic structure should be. So far we know that the poles in the residues on one side, on the negative real data axis, encode information about the low energy effective field theory, and we know that the high energy behavior is somehow encoded in the analytic structure on the other side of this complex data plane. But now naturally, in order to reconstruct the scattering amplitude from the celestial amplitude, one would compute some integral along some imaginary axis, along some contour in this complex data plane. And there are naturally two ways to recover the amplitude, right? One way is to close the contour on one side and pick up all of the poles. The other way in principle would be to close the contour on the other side and pick up all of the poles. So there might be some interplay between the UV and IR and somehow the way one closes the contours. But of course, in theories where there are black holes, so for example, or strings, like in the cases where which Andrea was considering, we know that, so in particular where the scaling amplitude is exponentially soft, we know that this implies some, that the celestial amplitude has a particular behavior at very large beta on one side of the axis, and one in particular, it sort of blows up with beta as you take beta to be very large and positive. But nevertheless, I mean, maybe there is, which, okay, there would be a contradiction otherwise. If this didn't happen, you would say that, okay, if we close the contour on the one side, we get something which should be the scattering amplitude. If we close it to the other side, we know that there are no poles in quantum gravity where there is this exponential suppression. So on one side, you'd get 0, and on the other side, you'd get an answer, right? So like, we know that something must happen at infinity. And so like, I just wanted to point out that perhaps what one should be thinking about is better to understand the this large beta behavior of celestial amplitudes in the same way where, you know, in the bulk, these dispersion relations, which allow you to connect, to make statements about this positivity and whatnot, some UV-IR relation, it's very important to understand the analytic structure at large. In that case, in momentum space, it's at large center of mass energy momentum transfer, but here it's kind of a different, the problem is formulated differently. So, but maybe there is some way to think about some kind of dispersion relations in this case and understand better what the inputs are in order to reconstruct the amplitudes.
Okay. So maybe I can ask a question, Anna. So I mean, naively we would think that the BMS symmetries would, you know, restrict the infrared sector of the theory. So even if we construct a dual theory just using the currents like the asymptotic symmetric current, then we know that, you know, it will give you the IR sector of the theory. But if you want to compute some UV scattering, then it's not clear if the BMS would have put any constraints, right? But I guess now what you're saying is that what you just explained, maybe you could use this UV-IR mixing to constrain the, right? I mean,
that's right.
Scattering. Like if I wanted to look at a large S fixed angle scattering, I'm not sure if BMS directly would play a role, right? I mean, but now it looks like you're saying that due to this.
Yeah, one point, okay, I don't really understand how BMS, I mean, enters in this discussion, but one thing which I should point out is that in usual momentum space, right, these dispersion relations are done at a large center of mass energy and fixed momentum transfer. But celestial amplitudes, you're not keeping this, there is no natural way to keep the transfer fixed. You naturally keep the scattering angle fixed, which corresponds to fixed cross ratio on the celestial sphere. So it's a really celestial amplitudes are really, from many different points of view, I think they capture complementary information to what, you know, scattering amplitudes are. And so understanding, yeah, it's a very different regime. So it'd be interesting to understand whether one can exploit properties of this to say something about, you know, a regime which is not that well understood in the bulk or in the usual formalism.
In 24 minutes, we are reconvening for the next.
Oh, so maybe we should wrap up now.
Yeah.
Okay. Well, so let's thank all the panelists once again, and all of you for a nice discussion.